then try and show you how integrability can show up in rather unusual problems. And since we are going to talk about quantum transport, and the intrinsic problem appears to be highly non-integrable, so because it involves chaotic motion, is quantum chaos, is related to quantum chaos. So how can you see integrability in a problem such as this? Okay, as another related topic that could be an alternative title to this talk is, since we are going to do supersymmetry harmonic analysis without superalgebra, that could also be the title, how to do superharmonic analysis without superalgebra. Okay, this is the typical setup. In a quantum transport, what you have is essentially you want to study how things like charge, heat, and spin can be transferred from one reservoir to another. It could be many reservoirs, but I'm taking here the simplest setup, just 2 reservoirs. And the reservoirs can have any type of phase in solid-state physics. So it could be a normal metal, could be a superconductor, it could be a magnetic material, a ferromagnetic, for instance. And there are a number of universal relations, integrability conditions, and very powerful mathematical structures that can be explored to find these analytical solutions. And much of them are hidden behind some very complicated, very convoluted algebraic structures, like what you have when you introduce supersymmetry in the problem. So I'm going to strip all that and show you how to do calculations in a way that all these structures becomes transparent, explicit. So to be more specific, and I want to show you an exact solution that's going step by step, every turn of the wheel I'm going to show you. And the specific problem is a chain of Andreev quantum billiards. Andreev quantum billiards is a structure in which superconductivity is induced by the proximity effect. And in order to close the gap, the proximity effect creates a gap in the excitation. For single particle excitation, you need to close this gap. And you can do this by choosing the pair potential in a way, by fine-tuning the pair potential in such a way that the excitation gap can be closed. That can be done, even experimentally. And this, in particular, doesn't break time reversal symmetry. So this is going to be important in order to have the calculations done exactly. Okay, let's start from the beginning. If you want to solve a problem such as this, and the first thing you have to do is find out what the symmetries that are going to be important in order to formulate the problem in a controllable way. And Freeman-Dyson gave us a complete classification of complex quantum systems that includes these quantum chaotic quantum billiards that I have shown you before in the transparency. And it involves this threefold way. Essentially, it has to do, there's a one-to-one correspondence with the associative division algebra, real, complex, and quaternions. And for a long time, looking at these symmetries, essentially time reversal symmetry, and whether or not you have spin rotation symmetry. So these 3 Wigner-Dyson ensembles were thought to be everything. So it was supposed to tell the whole story. But in the 90s, people realized that there are other classes of symmetries that come up from inclusion of things like particle-hole symmetry and sublattice symmetry that gave rise to a chiral class for the case of sublattice symmetry, and particle-hole symmetry gave rise to 4 more classes, the Bogoliubov-Dejean classes. So now you have 10, it's called the 10-fold way, and they are related to Cartan's classification of symmetric spaces. So there is a more powerful algebraic and geometric structure that gives you the reason, the mathematical reason why this classification works. Okay, but there is another connection that I think is even more powerful and has not been studied and developed to the level I think it could in order to find this algebraic structure that I'm going to strip the problem of, which is the connection between 3 different approaches to the same problem, to this problem of quantum transport, that involves, in one case, a nonlinear sigma model. There are 3 varieties of nonlinear sigma models. The supersymmetric nonlinear signal model, which is the one I'm going to show you connections to, and the Keldysh nonlinear signal model and the replica nonlinear signal model. They have different properties according to how you want to do the calculation. The nonlinear signal model is very good for non-perturbative analysis, for instance. And the other method is random matrix theory. So you could also say that much of the calculation I'm going to show you is going to be done in the context of random matrix theory, but in fact, we are going to use the nonlinear signal model in a specific representation in which the color flavor transformation, which is the exact connection between the nonlinear signal models and random matrix theory, can be performed in a very, very explicit way. So we are going to be using this connection, okay? But besides this, you also have a semi-classical trajectory-based method, and there are a number of very interesting results that people have been obtaining in the last few years. And they've shown that there is this diagrammatic expansion connection between this sigma model. There is an asymptotic equivalence that will have been shown in a variety of papers. But no one still has any general proof that in the non-perturbative sector, these three models are in fact completely equivalent. So there is this issue, these mathematical issues. Okay, but once you have the classification, a basic question is, how do you use it? How do you actually, in an actual calculation, how do you use the classification? So let's start with a very simple statement, a very simple problem, a very simple question. Suppose you have this structure that I've shown you before, a sample sandwiched between two reservoirs, and you ask for instance, the conductance distribution. What is the conductance distribution of a phase coherent sample between two normal reservoirs, just to make it simple? So what you have to do is, first you have to connect the conductance to some scattering quantities, like the transmission matrix or the eigenvalues of transmission matrix. And this is actually Landauer formula, a famous relation between the conductance, the charge conductance, also the heat conductance has a similar relation, and the eigenvalues of T plus, where T is the transmission matrix. So these are called the transmission eigenvalues. And what is known, and this is where the chaotic motion comes in, is that you have these transmission eigenvalues. They have a joint distribution that includes very, very high level of correlations. So the non-triviality of the problems comes from this high level correlations between the transmission eigenvalues. And suppose, also to make it a very simple statement, that you want to understand how this conductance distribution changes with the length of the wire. Suppose it's a continuous wire connecting these two reservoirs. And what you know is that what you have is, in this symmetric space representation, you have a diffusion, a free diffusion in the symmetric space. And the free diffusion in the symmetric space includes a Jacobian. And this Jacobian you can actually construct directly from the Cartan's construction or formulation of symmetric spaces. So if you consider, for instance, hyperbolic symmetric space, non-compact symmetric spaces, then this function is hyperbolic sine. If it is a compact space, it's just sine. And if it is flat tangent space, then it's just a linear function. So, but the structure is the same, and you can get it from the Cartan construction. So you know the equation. You can simply write it down. This is free diffusion. This is actually a Laplace-Beltrame operator. And what's left here is two things. One is very simple, is what are these exponents here? They are roots of a Coxeter group, but this is a technical statement. But in fact, you can actually read it off a table where you get the universality classes and symmetry parameters. So for each of the universality classes, the three Wigner-Dyson, the three Kairos, and the four Bogolov-Dejean universality classes, you have the values of alpha, beta, and gamma. So you don't have to worry about it. What you really have to worry about is how to solve this problem. Okay, you formulate. So what the classification in symmetry classes gives you is the equation, but does not give you any hint as to how to solve it. So this is what I was concerned about a few years ago. I started then a program, it was in 2006, to make a new classification, an alternative classification, that instead of looking at the algebraic properties or the geometric properties, I looked at the solution problem, solution techniques. Can I classify the problems in terms of its solution complexity? So from the simplest one to solve to the more complex one. Can you make such a classification? In a way that, once this is done, you get, of course, all 10 symmetry classes. It has to accommodate all the classes that are known, but also that gives you a general approach to solve the diffusion problem, which is how to solve the diffusion problem, the heat kernel problem, by harmonic analysis. That's how you solve it. You find the eigenfunctions and eigenvalues. So you have to find a way to perform these calculations in a systematic way that you get from simple to harder problems. Okay, once this is done, the idea, the basic idea is to find a new type of coordinate, and the classification is similar in spirit in terms of mathematical physics. Is instead you can classify special functions in terms of their connections to symmetry groups and symmetric spaces, or you can classify these special functions in terms of its differential equation. So it's Fuchs classification. So they are related to Fuchsian functions. So we are doing something similar, okay? We are trying to classify the problem in terms of the differential equation that we want to solve, in terms of its pole structure and so forth, instead of the geometric structure. So we are going to strip off the algebraic structure and see what is the price that we pay in doing this. Okay, we still have of course, the interaction terms. I cannot get away with it. So it has only the simplest form. This is how the variable x is defined. It's defined in such a way that the Jacobian of the transformation from, if it is a matrix, from the non-diagonal representation to a diagonal representation. When you do this, you get this gestural form or Jacobian, and the weight function. Okay, so here is the table. So this is all symmetry classes, all problems that you can formulate in terms of this tenfold way classification, gives you a collection of functions, W, S, and R is defined in terms of W and X. So this is the two relevant columns. This is the interval where the variable X is defined, and here are all the classes. And on top of the classes, we can also make a classification of some classical random matrix ensemble, like the Gaussian ensemble, the Laguerre ensemble, Wishart, which you can write in terms of Wishart matrices, and the Jacobi ensemble. The three ensembles can also be classified in terms of the multivariate extension of Hermite, Laguerre, and Jacob polynomials, which you can relate to Jack polynomials and structures like that. I'm going to mention them later on. Okay, so this is the table. So what you have to do is to find your W and X functions from this table, and then you try and solve the problem. Okay, once this is done, the next step is to find you still have to find the complete set of eigenfunctions and eigenvalues, okay? So the next step is to perform a similarity transformation. It's called the Sutherland transformation. So you start from, you go from real to imaginary time. This is very simple. It's a Wick rotation. But then you use the Jacobian and this weight function to make these transformations where now psi is going to, this is where integrability is going to come into the problem. You get a Hamiltonian problem. Now it's a Hermitian. The Fokker-Planck operator is non-Hermitian. So you transform it. Essentially, it's a technique to transform a non-Hermitian into a Hermitian problem. And what you get is a Hamiltonian of Kalojia-Sutherland-Moser type. So that guarantees you, that's been analyzed in the literature, is well known. It's integrable, fully integrable Hamiltonian. So you can construct all the eigenfunctions and all the eigenvalues. And so the problem is essentially reduced to solve this. The exact eigenfunctions and eigenvalues of H can actually be obtained by making transformations such as this. And the result for all the classical ensemble have been studied, is in the literature. We have also made some contribution to this. And these are old papers, and you can relate it to Jack-type multivariate extensions of classical orthogonal polynomials. So it's a complete construction, okay? You get a Rodriguez-type formula. It's called LaSalle-type formula in the technical literature, but you get them, okay? Explicit. Okay, once this is known, okay, does this solve the problem? Not really. And the reason is having, let's go back so that you understand what I'm saying. Having this function, suppose you are looking at a quantum dot. In a quantum dot, you know P. For a quantum item, we still have to solve a problem. Okay, you have to find the eigenfunctions and eigenvalues. But for a quantum dot, a single dot, you actually know P. You know this function. But you still have to do this integral. And this integral is not simple. It's not easy to do. So then the problem becomes related to how do you perform such an integral in terms of once you know the eigenfunction and eigenvalues. This is where supersymmetry comes in. Because you can transform the problem, make a useful representation of the initial problem in terms of this matrix transform. So this is related to a technique of solving differential equations like the hypergeometric differential equation in terms of integral representation. So what you have to do is choose a kernel and you perform, you substitute this tentative solution into the differential equation and you get an equation for the image function. And this equation is supposed to be simpler than the hypergeometric equation, original hypergeometric equation. You solve this, choose the integration contour in such a way that you get all linearly independent solutions, and in the end you get a very, very explicit and simple representation for the hypergeometric functions, for instance. But of course it works in many other different problems, and here is how you choose the kernel. It's a generalization of the Euler kernel that's used for the hypergeometric function. We know that's more or less in the class of the hypergeometric function because of the Fuchsian representation that I talked about earlier. Okay, so use this generalization of Euler kernel, and then we perform, there is a connection between N1 and N2 related to the beta symmetry index that I showed in the table for the different symmetry classes. Okay, so now we calculate the image functions, which is this W. And here comes an interesting surprise. At no point, at absolutely no point in the derivation, I have talked about supersymmetry, superalgebra, superharmonic analysis. There is no direct connection to supersymmetry. Nonetheless, if I look at the image function and the dual Fokker-Planck equation, then we see precisely what I would get if I used the supersymmetry connection or the color-flavor transformation. And in particular, what plays the role of the Jacobian, that is the interaction between the levels or the position of the fictitious particles, is the Berezinian. Everyone who knows supersymmetry would recognize this as the Berezinian. So that is, if you diagonalize a supermatrix and you go from an arbitrary representation to the diagonal representation, the Jacobian is replaced by a Berezinian. Okay? So it has precisely this form. The other functions are not really relevant. They are consequence of the structure of the problem. And the other interesting thing is this minus sign here in this connection with the index beta. So it shows that I have two types of particles. Two types of particles. So it's like a one-dimensional semiconductor with one band, upwards band and a downwards band. And this is precisely what I expect from supersymmetry, because fermions and bosons, they see in supersymmetric spaces different types of geometry. So the fermions see a compact space, and the bosons see a non-compact space. So this is how the formalism is telling you that they are different. So I have to choose a compact domain for the variables n0 and a non-compact domain for the variable n1 in order for the solution to make sense mathematically. And that's how the problem is telling me that there is a hidden algebraic structure related to supersymmetry. Oh. Why it's one dimension? Just a chain. You're solving a chain. So it's no, yes, that's true. There is no spin statistic connection. Okay, next step. This is still the technique. Okay, I'm presenting you the technique. Then I'm going to show you how to solve the specific problem with the technique. So the last step of the technique is to find the correspondent problem in dual space. We already seen that solving the problem in original space doesn't help much because we still have to do the integrals, and the integrals are very hard to do. And we want explicit solutions. So what you do is you perform a collisional Sutherland-Moser type transformation. And there is a subtlety here. Oh, sorry. There is a subtlety here, is that everyone who has done supersymmetry calculation must remember that there is one aspect of supersymmetry calculation that makes it very hard to do calculations such as this, where you have a very arbitrary number of coordinates for fermions and bosons. That's the large number of fermions and large number of bosons. And the reason for this is related to what's called the surface term, the Parisi-Suhler's effect of surface terms. And the problem with them is that there is no general rule how to calculate these surface terms. They just pop up in the calculation. You have to calculate them, otherwise everything is going to be wrong, of course. And there is a contribution that comes from the Berezinian, so that's controllable. So it's part of supermathematics. And these other ones is a removable singularity in the supersymmetry representation. It has to do with the nilpotence, okay? Because Gaussian variables, the square of Gaussian variables is 0, and you have this nilpotent contribution. It's very hard to account for them. So I have to deal with this, and there is a receipt for doing this as well. Okay, so here I'm not concerned about this at this time. So there is a constant term that should be added to the similarity transformation. I am going to solve it problem by problem. And in the end, what you get is a dual Hamiltonian that's also of Colosio-Sutherland-Bose type, is also an integral Hamiltonian. And we know that I can find the eigenfunction, I can construct the eigenfunctions, proceeding essentially mutatis mutandis with what we've done before. And in principle, for the classical ensembles, we get deformed versions of the multivariate classical polynomials. This has never been done, nonetheless. So we know that's doable. We know that's, in principle, systematic. But what we found in the literature, especially in the Russian literature, are existent proofs. So people have shown that these polynomials exist. They form a complete set. They are generalizations of the Jack polynomials and hijack polynomials and related polynomials. But I've never seen a complete construction of these polynomials so that I could use in the calculation. So, but it's doable. There is nothing that's telling me that that's beyond the reach of current mathematical analysis. Okay, this is the method. What it's telling you is that in order to solve a complicated diffusion problem in symmetric space, all you have to do is look at the dual space. And perhaps, if your question is simple enough, the problem in dual space can be very simple. And this is precisely what I'm going to show you now. So let's go back. So you have this general method of finding a solution to integral problem. And let's go back to our original problem. So I have a chain of Andreev quantum billiards. And in order to set up a simple problem, I'm going to fix the chemical potential to be the same in both terminals and only have a temperature gradient, so that what's being transported here is actually heat. And superconductor, of course, does not conserve charge. So if you want to probe transport properties of a superconductor, you have to look at things like the heat transported by the quasiparticle, which are Bogoliubov quasiparticles. Okay, so the next step is to ask what is exactly that you want to solve. It turns out that the conductance distribution is a very hard problem to find exact solutions. You can find asymptotics and even numerics. You can work it out. But in order to get complete solutions. What I mean complete is I want functions that I can actually find asymptotics, understand the entire behavior, and plot it, see it, give it to experimentalists, and say, this is what we predict from a system that has this structure and this geometric properties. So in order to achieve this, we have to select what is the quantities that we actually want to calculate. And here we've chosen to calculate the 3 moments of the heat conductance, the first 3 moments. Why the first 3 moments, you may ask? I'm looking for the simplest solvable problem. And the simplest solvable problem involves, in dual space, going back here, it's important to understand because that's the very reason why the method has been developed, okay? It has developed because I want to create a hierarchy of solvable problems and put the complexity of the difficulty of solving the problem as a way to select positions in this hierarchy. So the simplest problem is if n1 is 1 and n0 is 1. Okay? You agree with this? Because we get the... and also beta equals 2. With beta equals 2, all the interacting terms disappear. This is a constant. So you get a free Hamiltonian. So just by looking at the problem of the Hamiltonian, you can directly see what's the simplest construction. And what is that you can do with problems such as this? You can find the first 3 moments of the conductance. Why can you find the first 3 moments? I have to go a bit forward. Okay, I'll go back soon. Here. The reason you can do this is that the W function, that's the dual of this integral transformation, can be seen as a generating function for the conductance. Okay? So the first 3 moments of the conductance are actually derivatives of this W function. So you have to construct this W function. Let's do it. Okay. So the first 3 moments of the conductance is just these integrals. You have to find P of t as a function of tau. Tau is the length of the wire. Okay, if the wire is, the mean free path for elastic scattering in this problem is essentially the size of the quantum dot. So if the length of the wire is smaller than the size of the quantum dot, then you have to use the probability distribution of the quantum dot. And that you can get from a maximum entropy principle. That's been done in 2010 by Bineka and a collaborator. So I didn't put the reference here, but this is in the literature. And you can get, and the nu is the difference between the number of open scattering channels in left and right lead, and beta and gamma you can take from the classification table. So there's no problem with the index. Okay, but you still have to do the integral, okay? The integral has to be done. Sorry, yes? Yes, yes. Beta is given by this. Here. So since we are in BDG class, I'm going to get to take beta equals 2. These 2. Yes, yes. Beta equals 2. The same beta. Here. So beta equals 2, which means that all these 3 terms that involves interaction disappear. So I get free particles, free bosons and free fermions. Okay? Incidentally, the problem, since I'm trying to solve the simplest problem, you can find any moment of the conductance because it's still going to be free fermions and free bosons. So you get a determinantal process, like you were talking earlier. So you get that determinant process that you can also solve. Only a supersymmetric version of the determinant problem. Okay, so now you get this. You have to do these integrals, and let's start by performing the calculations in this procedure, implement this procedure. So the way you do this, the first step is you relate the x variable to the physical variable. The physical variable here is the eigenvalue, the transmission eigenvalue, tau. So the connection can be very simple. It's very simple to find this. There is no difficulty whatsoever. Once you have the x variable, the rest is fixed. You go into the table and you get the W for the scattering matrix or the transfer matrix. Here we have to combine these 2, the scattering and the transfer matrix, because the scattering matrix is going to be the initial condition. So that the wire becomes a dot when it's short enough. And here is the x variable. So everything is in place, and here's the initial condition. So from a mathematical point of view, we have to solve a diffusion problem in a symmetric space, in a large symmetric space, with a quantum dot initial condition. All right, let's do it. The way to do it is to go to the dual space. This is where the nonlinear sigma, the supersymmetric, the one-dimensional supersymmetric nonlinear sigma model lies. And there is one interesting thing here. Mind you, we have 10 classes, okay? 10 classes. This gives you 10 nonlinear sigma models. Each one has its own algebraic structure. And in order to perform a calculation like the one I'm going to show you, you had, in principle, to do all of them. Of course, since we are only selecting 2 special cases, because we make an order in terms of complexity of the problem, then only 2 nonlinear sigma models had to be done. But still, you have to do superharmonic analysis in 2 nonlinear sigma models. And this method allows you to combine the 10 classes into a single equation. Okay? It's important to have in mind this incredible simplification. And at some point, you have to pay the price for doing this. Okay? There is no free lunch, right? So there has to be a price. If you want the wonders of supersymmetry without having to pay the price of supersymmetry algebra, there has to be something that you have to pay at some point. Okay, now you perform this integral. And what it does, it gives you a Fokker-Plonk equation in this, in the compact and non-compact sectors of the symmetric space, the supersymmetric space. And here's the Berezinian. It's very simple because you have just one fermion and one boson, so it's very simple, the form of the Berezinian. And here's the initial condition written in terms of W. Okay, now there is one step. Since I'm telling you every turn of the wheel, I have to tell you how I did the 13. Not yet, sorry. The 13 calculation involves a generalization of Selberg's correlation integral. So this is, I'm going to tell you just using words without showing it as explicit in the transparency. But here I'm going to concentrate on finding the complete spectrum, okay, the eigenfunctions and eigenvalues. So here comes the one. This one is the solution. This one here appears to be very simple. Just you put it by hand. But this is the contribution from the Pauli-Suller effect of term. Okay, so this is this complicated surface term that you cannot find a general representation of. And this is the contribution that comes from the Berezinian. So the Hamiltonian, as we have anticipated, since we've selected the simplest solution, it contains only 3 particles. And the set of eigenfunctions now are very simple, because the compact part, the fermionic part, contains only Legendre polynomials. And the non-compact part is it's a hypergeometric function. So there is no particular surprise here. Okay, everything is under control, so we have this normalization factor and related to the orthogonal polynomials, that's well known, and also this function is related to the asymptotic properties of the hypergeometric. This is also known because it says this hypergeometric function comes from a scattering problem. You can use this Dirac criterion to make this delta function in energy. This is how you fix this parameter, this function. This Dirac delta function in energy for scattering eigenfunctions. This is Dirac's rule for constructing continuous spectrum. Okay, now the next step is how do I get the initial condition for the dual space? Here is the part that you have to be very careful because you want to do the calculation, the integrals. And there is a connection that's still under work that is going to systematize this part as well, which is a connection with Maya G functions. Do you remember when I said that what we are doing is a classification in terms of generalization of Fuchsian functions? One of the ways of doing this is by using Maya or Fox H functions, Maya's G function or Fox H functions, which makes a representation of essentially every classical function, special functions that you know of. You can write in terms of the Mellin-Barnes representation. So we can make a multivariate extension of the Mellin-Barnes There are some attempts in the literature in doing this, so we have to make some contribution in order to make it useful, which the matrix-valued Fox H function or Meyer G functions. And by doing this, you can write all Selbach's correlation integrals in terms of these Meyer functions. And this is one way of performing the integrals. In the end, we already know, in this case in particular, that because of there is a connection with Harishchandra integrals, so we know this is a matrix-valued hypergeometric function. So this Harishchandra integral tells you this is harmonic analysis in classical spaces, okay? In non-compact classical spaces. It shows you that this matrix-valued hypergeometric function can be written in terms of determinant of hypergeometric function. So by doing this expansion, since I have only 2 degrees of freedom, 1 Fermi and 1 boson, this determinant, which would be a complicated calculation in the end, becomes just a single line and a single row. So I can use a representation that's very simple, very similar to what you get in random matrix theory. Okay, so it's a sum of products of functions. In random matrix theory, it's just polynomials, and here we have one polynomial written here in terms of hypergeometric function, and the other is the function. So this supersymmetry gives this combination between non-compact and compact. Random matrix theory apparently sees only just one type of space. Okay, that's for the initial condition. Let's now get to a spectrum. So in order to do the complete honest calculation, you have to construct the propagator, the Green's function. But since you have all eigenfunctions and eigenvalues, you can actually do this explicitly. And here is the Green function. I didn't mention much about the eigenvalues, but here they are. So this is the part. Since it's supersymmetric, you combine the fermionic contribution, which is discrete because the fermionic space is compact, with the bosonic contribution, which is non-compact. Okay? So you get a combination of these two. This you get automatically from superharmonic analysis. And the Green function satisfies the usual initial conditions, so it's delta function at initial. For t equals 0, this is the y of length 0. And the complete solution is written then in terms of integral of this g function, which is here. And we have to plug it here and use this w had before. Here. Okay? Okay, at this point, you might say, okay, this is hard because we have to do these integrals, and these integrals are particularly appear to be difficult. But then, this is where the Meyer G functions comes to your help. And that also gave us the idea of bringing in the Meyer G functions much earlier. Because at this point, we would already recognize, we write this in terms of Meyer G functions, and most of the difficulties in making the integrals will disappear at this point as well. But since we didn't do it, we have to perform these calculations, and you can use a lot of identities from the theory of Meyer G functions, and here's the explicit solution. Okay, so this is the complete solution of the heat kernel in the dual space, in the supersymmetric dual space. It has a combination then of discrete sum of the fermionic sector and the integral in the bosonic sector, and these two C functions that are related to gamma functions. Okay, since we have the complete answer, what we want to do is to calculate the observables in order to give the experimentalists something to compare to. And the average thermoconductance, the second moment of the thermoconductor, the third moment of thermoconductance can be calculated by simply taking derivatives of these generating functions, and here is the explicit solution. And that's it. That's how far you can go. You can get explicit expressions for the heat transfer from one reservoir to the other through a series of quantum dots connected. Here we took the continuum limit, mind you. So it became actually a quantum wire connected to dots. There is this continuum limit step that we did in the middle. Right. Let's now use. Since you have an explicit solution, you can use it to analyze what is that you predict, what is that you get from the physics of the problem. Here's the mathematics stopped. Let's start with the physics. Okay, if you look at the large asymptotics, that's what's happening if you have a very long wire. And here comes a physical interesting result. It's not that much surprising because some of the results have been anticipated for a single wire, that you have no localization. So there is no localization in this problem if you are in the situation where you have time reversal symmetry and spin-orbit coupling. And that, for a single channel, I'm going to make a comment that has to do with the emergence of Majorana modes. So this is how it has been interpreted. So heat is actually transported by these Majorana modes. For a single channel, there is no, for many channels, it's not so obvious that you can invoke Majorana modes, especially because then you need to replace the conductor. So here we have a semiconductor with a proximity effect inducing superconductivity. In order to have Majorana modes, you need a topological superconductor, which you can get by using the matrix as a topological insulator. So the surface is a special kind of metal, and the proximity effect in the surface of topological insulator has these Dirac cones, and because of this, you can get this. This has been shown. Then you can get these Majorana modes at the edges, okay? Two Majorana modes at the edges. And if you then connect them in a gradient of temperature, then they will be the carrier of heat. This is one way of understanding localization, but here we have the usual localization. So the system goes from ballistic to metal. So we have three phases: ballistic, metal, and localization. In case of C1, here I'm using the Cartan classification. So in C1, we have this ballistic, metallic, and localized behavior in smooth crossovers. And for class D3, we don't have localization, so it goes from a ballistic to a normal metal to a anomalous metal. Okay? And this should be contrasted with what you get for a normal wire. This is a calculation they have done in 2002, long time ago, using supersymmetry, using a harmonic analysis. So I know how to do the calculation the hard way by using supersymmetric harmonic analysis. It's very hard. And by doing this, using these techniques, where you strip off all the algebraic, supersymmetric algebraic structure. Yes? Here is variance and third cumulant. And the single barrel is just moment. Okay? Sorry? Cumulants, yes, cumulants. So cumulants or moments. Okay? All right. You have an explicit solution, then you can make a graph, okay, of the entire regime. This graph can, this is how it's done. Here, n equals 1 is very interesting because in n equals 1, it's proven, you know that there is this Majorana mode, and people are looking for signatures of Majorana modes in condensed matter physics, and this is one system where you can look at it. So you find, if you find, look at the difference between G3 and the third cumulant for class D3 is where you have this Majorana mode, and the other ones where you don't have. So this is where you have the topological superconductor. It's one realization, topological superconductor. So you see that you have this inverse square root with length. So this is a signature. So if you realize this quantum wire in a lab, so you can, and if you see this one over square root with length dependence, then you can say for sure that you have a signature of condensed matter Majorana mode. And why do you need D3? Let me go back here and explain it a little bit more. Why in n equals 1 you need D3 in order to see the Majorana mode? The reason is that the Majorana mode is a coherent superposition of electron and hole, but it has to be in the same spin band. Underlevel reflection doesn't do that. So simple underlevel reflection doesn't solve the problem because it is a superposition, it's a singlet, okay? So it's a superposition mixing two spin bands. So you have to connect these two spin bands, and this is what spin-orbit coupling does. So it connects the two spin bands, so you can get superposition, non-trivial superposition, of this zero energy mode, and that's going to give you a real scattering matrix and real wave functions, okay? Which is what you expect for a Majorana mode. So this is how you realize the Majorana mode in n equals 1. For n bigger than 1, there is a problem that the Majorana modes, that, for instance, if you get n Majorana modes in each edge of the wire, you need to mix them, and for that you need chiral symmetry. Of course, you can formulate the problem in terms of chiral symmetry, but then there is a problem. If I want to solve it from the integrability point of view, okay, it's still integrable. You still can do it, but it's not the simplest problem. Now we know this because we have this classification. So if I look at this here, so from the chiral, okay, let's go back a bit more here. So the problem that I need to solve is this one, chiral. I need a time reversal symmetry, and I need spin rotation symmetry. Yes, yes, so beta equals 1. So I know that in this problem, because beta equals 1, I need it to be chiral here. So I have to solve a problem with interacting fermions. Okay? So it's the same problem, but it involves interaction. You have to, a similar problem, but you have to use these deformed versions of multivariate classical polynomials. They are not available in the literature, although the existing theorems are there. But you have to construct them, otherwise you won't get exact solutions. So this is why we postponed this to the next problem involving chiral symmetry. Okay, so this is for n equals 1. So you have so you have the exponential localization. So it crosses over from ballistic to metal. N equals 1, there is no metal, sorry. It crosses over from ballistic to insulator, and here from ballistic to anomalous metal. But for n, for arbitrary n, and here we increase, this is a very interesting plot, because it shows how the solution goes from this quantum wire crossover to a single wire. So the n equals infinite limit is the thick quantum wire. So the problem that you can solve using simple F-et-al symmetry approach. Okay? You don't have to use all this complicated, convoluted construction. You can use simple, because it's quasi one-dimensional, then the thick wire is a much simpler problem. And this has been solved, not for this class, for the normal class by Zimbauer using harmonic analysis, supersymmetric harmonic analysis. So this is a known solution, okay? So here I'm showing how you go from one to the other. And the small n limit is called also the extreme, the time, okay. The 3 minutes? 2 minutes? The extreme quantum limit. So experimentally, it's much easier to investigate the extreme quantum limit rather than metal. Okay, let's go to the conclusion. So we have obtained exact expressions for the first 3 moments of the heat conductance of a quantum chain crossing over from a superconducting quantum dot, a chaotic superconducting quantum dot, to a superconducting disordered quantum wire. And we've seen this striking effect of total suppression of the insulating regime. So there is no Anderson localization in the problem. If you have broken spin rotation invariance, and this is observed at very large length scales. And for a single mode, you can, if you realize the system in a topological superconductor, I can interpret it as a signature, a condensed matter signature of a Majorana mode. There is and as a final remark, there is this beautiful, powerful mathematical structure in the solution that may prove useful in establishing equivalence proofs between the various non-perturbative approaches, but also it shows in a very explicit and accessible way the structures that are hidden in the supersymmetric calculations, which are very daunting and hard to do. And they have beautiful mathematical structures that people simply don't look or care about them because they are hidden. Okay, thank you very much.